Cisco Certified Network Associate Day 54. Welcome back everyone, I'm Imran, Rafai, your trainer for this entire series. Today we're going to discuss about network architecture. Like always, before we go ahead, click on that subscribe button and don't forget to click on the bell icon. So when you click on the bell icon, you would see an option which says all. If you click on that, you will be notified anytime we add a new video. Also, while you're at it, do not forget to click on that like button. If you find our training useful, I would appreciate if you could give me a recommendation on LinkedIn. Let's assume this is a small city, and in these office areas, we have our office buildings. So let's assume we have these three buildings which are part of our office. Let's call this building A, and this building B, and this building C. Let's assume our building A is our head office. So we have internet connection coming in. So let's say it's connected to the router. From the router, we loop to another switch in building A. From building A, we loop to the switch in building B. From building B, loop to the building C switch, and then another loop to the second switch in building C. Let's assume each of these buildings have 100 users, and these switches, of course, are connected to end devices. So you would have it connect to maybe a desktop computer, maybe laptop computer, right? Or maybe it's connected to a wireless access point. And of course, if you know a wireless access point, you would have multiple devices that would be able to connect through wireless access Wi-Fi. So each of these buildings are connected to end devices or endpoints. It could be servers, desktop computers, laptops, mobile phones, or anything. But this is not the right way, especially if it's a big campus LAN like what we're talking about with multiple buildings. This is definitely not the way you should be designing networks. This might work for a small building, but still this is not the way. What Cisco recommends is to use an architecture called as 3-tier, right? 3-tier, 3-tier. This is British and American. So I'm not going to get into that controversy, but you could call it whatever you want. I'm going to call it 3-tier. So in 3-tier architecture, what Cisco says is you need to break up your network components into multiple levels or multiple tiers. So Cisco says you have certain switches which we call as the access layer, right? Access layer, like the name says, the main function of the access layer switches is to connect the end devices, right? So you could have it connect to different endpoints like we discussed in the last slide. So we could have servers, laptops, wireless access points connecting to other wireless devices, right? So the main function of the access layer switch is to get these end devices or endpoints to the network, right? Just connect them to the network. That's all an access layer switch does. So all the access layer switch does that work. So once that happens, all these access layer switches are connected to another layer called as the distribution layer, right? So the distribution layer has slightly better switches. These switches really typically this is where you would do all the logics like access lists, VLANs, and all the logic in the network happens here. This is the layer where the switches will start doing all the logic, right? The access layer switches will just do that, connect all the endpoints to the network, and distribution layer switches will aggregate all those access layer switches. So each of those access layer switches are connected to each of the distribution layer switches, and the distribution layer switches by itself would be connected in an ether channel. So you will have ether channels between the distribution layer switches. So once we have this ether channel, if you know anything about like we discussed in one of our last videos, we spoke about a concept called STP or spanning tree protocol. So once you have an Ether channel, this, right, this becomes a loop, right? This becomes a loop. That means STP will now start blocking one of these links. So each of these devices, access layer switches connecting to the distribution layer switches, one of the links would be in blocking state to prevent loop, right? So STP will start doing its job, and one of the ports will go off. Now the next layer is called as the core layer, right? So the distribution layer will be connected to the core layer. So each of the building has similar things. So you have this as the access layer, and this is the distribution layer. Similarly, this is the distribution layer, and this is the access layer, right? So once the distribution layers, again, these are Ether channels. So once these devices are connected to the core layer, one thing we should know is, by looking at this, that there is a lot of redundancy, right? A lot of redundancy, because a lot of links in this diagram would be in blocking state because of STP. That means if, let's say, one of the core switches were to fail, the network would still work. So for an end user, let's say somebody using this network, for them, it really wouldn't make any difference, because they wouldn't even know that one of the core switches failed. This could also happen if one of the distribution switches were to fail. An end user would never know, because the network will still work, right? This is the beauty of the three-tier architecture. Because of redundancy, network will always work, and an end user will never know what is happening. Now, if you were to represent the three-tier architecture in a form that you would see in many places, it is going to be like this, where you will see that the access layer is at the bottom layer, right? The layer above that is the distribution layer, and the layer above that is the core layer, right? So this is the access layer, this is the distribution layer, and this is the core layer. Similarly, this is the access layer, and this is the distribution layer. So in Cisco world, what we would do is, this would be one pod. So this would be one pod, and this would be another pod, right? We could call this pod A, and this would be pod B, right? So this would be pod A and pod B. But if you look at, this would be access layer switches, this would be, or these would be distribution layer switches, these would be distribution layer switches, and this would be access layer switches for this pod. And of course, both these distribution layer switches are connected to the core layer switches. One thing that we need to understand is, at this point, so the distribution layer, whatever happens below distribution layer, that is between access layer and distribution layer, works in layer 2, right? Layer 2 between these 2 points. And whatever happens above distribution layer happens in layer 3, right? So when you know that layer 2, that means STP is going to work, and because STP is working, these links, or rather one link, will always be in blocking state because of the loop. Another slightly simplified version is called as the two-tier architecture. Again, like I said, British tier, whatever you want to call, two-tier architecture. Now, the two-tier architecture is also called as collapsed core, right? Collapsed core. That's because now in this, the distribution layer and the core layer has been collapsed to form the core layer. So the core layer in a two-tier architecture is actually nothing but the core layer and distribution layer of the three-tier architecture combined together, right? So this is the core layer, this will be the core layer, and this would be the access layer, right? Now, one thing that we need to understand between the difference between layer two-tie architecture and three-tie architecture is in two-tie architecture, the communication between access layer and core layer is working in layer 2, right? Because this is working in layer 2, two-tie architecture again has the same problem of STP. That means one link in each of these cases will be in blocking state, right? It will be in blocking state because it is working in layer 2. Another architecture that you will see is called as spine leaf, right? Spine leaf. That's because these are spines layer and this is the leaf layer, right? Main difference between the two-tie architecture and spine leaf architecture, I've seen a lot of authors say that two-tie architecture is exactly spine leaf architecture. Well, it is not. For one, the communication between the leaf and spine now takes place in layer 3, which means we do not have to worry about STP, right? That itself now adds bandwidth because now each of these, now if you look at these, this is full mesh, right? Full mesh. Now what does full mesh mean? That means each of these devices, each of these leaf devices are connected to each of the spine devices. And because there's no STP, each of those links are used in communication. Now, when the three-tie architecture and two-tie architecture was introduced many years ago, typical communication was always between server and the WAN connection, right? So if you look at from a geographical point of view, the WAN link or the internet is north, and the server, because it's at the bottom layer, is south, right? So these three-tie architecture and two-tie architecture were very efficient for north-south traffic, right? If the traffic is going from a server or endpoint to the internet or to the WAN link, then two-tie and three-tie architecture was very efficient because, like I said, because of the redundancy, you would always have access to those links. But for traffic between endpoints, like for instance server to server, right? Because of, again, if you look at geography, this would be west and this would be east, right? So any traffic for what typically you would call the east-west traffic, so traffic between endpoints, the three-tie architecture was not very efficient, right? So you would have more east-west traffic in a data center, right? Data center, and typically you would find spine leaf architecture used in data centers, right? So if you have more of these east-west traffic, spine leaf is the recommended architecture to use. Before we go ahead, let's look at the evolution of a server, right? Evolution of a server. So many years ago, when we started using servers, you would use a desktop computer, slightly more powerful desktop computer, where you would install your server operating system and the server function. So it could be maybe a file server, it could be a web server, it could be a database server, it could be a media server, it could be any type of server. Like I mentioned in the last video, server has nothing to do with the hardware, it's the software, right? But of course, because server, you have a lot of devices connecting to the server, you typically would give it a very powerful hardware, right? So when you have it running as a server, you don't really need the keyboard, the monitor, or the mouse, right? So it evolved from having a full-fledged desktop computer. You started using servers with only the CPU. Eventually, it evolved. Form factor went from a CPU to what we call as the blade server. So a few years ago, Cisco introduced a concept called as the blade server. Now, blade server is something you could put into a rack, right? In the rack, you could have maybe 10, 20, or 30 blade servers. And then in a data center, you would have multiple racks with multiple blade servers. Now, One thing that's common, whatever the form factor is, that each of those, whether it is in a CPU form factor or in a blade server form factor, that each of those servers have these components, which is very, very critical. One is it needs RAM, it needs CPU, it needs some sort of storage, either it is hard disk storage or it needs solid state drive or SSD, right? This is very, very critical for any type of a server. Now, if you look at a few of the marketing materials for Intel CPU or AMD CPUs, you would see that CPUs today come in quad core. Quad core means it has 4 cores, or maybe even octa core. Octa core means it has 8 cores. Now, if you were to run a visualization software to monitor your device hardware, even your laptop or on your desktop computer, if you were to run a visualization software, you would see that most of the time, even a Windows 10 or Mac operating system or Linux operating system, most of this time, when you don't have too much load, only one of the core is being used. Of course, this has to do with battery optimization as well. If you don't need 8 cores to run at the same time, why run all those cores? So they will shut down those cores and only one of the core would be working. So that's what happens in a server as well. Most of the time when there's not much load, only one core works, right? So what I'm trying to say is one core is enough for a operating system to run, right? So a few years ago, a concept called virtualization, right? I'm sure everybody, even people just getting onto the IT industry would know this concept. You know, people are talking about virtualization, virtual servers, virtual switches, virtual machines, right? So what is virtualization? Virtualization is a concept where you take the hardware. Let's assume the hardware, we have a hardware with 64 GB of RAM, octa-core CPU. We have, let's say, 500 GB of SSD and 2 TB of hard disk, right? So we take this hardware, right? This hardware, physical hardware, and on top of that we run a software called hypervisor, right? Hypervisor. What you do is hypervisor, like hypervisor, maybe like ESXi server, you run the hypervisor software. Once you run the hypervisor software, what it could do is it could take this physical hardware and break it into smaller units and build virtual machines. So you could go to the hypervisor and say, give me a virtual machine with 2 core, right? 2 core out of the 8 cores, 8 GB of RAM, and 10 GB of SSD, right? You could have this, that's a virtual machine, and you could maybe run any operating system. You could have another virtual machine. It says, maybe you could say, give me a 4 core, give me 16 gig RAM, right? And maybe 100 gig of SSD, right? You could very, very easily configure this. Now the thing is, you could log into each of these virtual machines. Maybe you could have Linux, or maybe you could have Windows Server, right? You could have this. Now don't get confused with dual boot. So you would have a concept where you would have a Windows machine dual booting with Linux, right? When you do dual boot, the difference is you shut down one operating system and you load the other operating system, and each of these operating system has access to the full hardware, right? It gets access to 64 GB of RAM, it gets access to 500 GB of SSD, it gets access to 2 TB of hard disk and 8 cores, right? That's if you do dual boot. But if you're doing virtual machine hypervisor, this Linux operating system will have access only to 2 cores of the CPU. These are virtual cores. Of course, it's broken down. It's not a physical 2-core chip. It's an 8-core chip, out of which 2 cores are given to Linux. It has access to 8 GB of RAM and 10 GB of SSD only, right? It cannot get anything more. And both the softwares, like if now in this case we have 2 virtual machines, but if you have 10 virtual machines, all the 10 virtual machines can run simultaneously, right? So because it's a server, you could have Linux, you could have Windows, and you can have all of them running. And from a laptop, right, you could connect to them over SSH, and you can manage, right? It's perfectly fine. It will work. And this is the concept of cloud, right? In cloud, even if, let's say, for instance, if you go to AWS is Amazon's web services. So if you go to AWS's website, sign up there, and AWS gives you, I think, a very basic server that you can configure. And for 1 year, you don't need to pay any money. You could do that, right? So if you go to AWS and you configure a machine, let's say with 4 cores, 8 GB RAM, and let's say 100 gig of SSD, right? You configure on AWS. Now you can go to your computer, right? And through your computer, you can connect to that virtual machine. So it's as good as having a virtual machine in your office, but instead of being in your office, it's a virtual machine that's sitting on Amazon servers somewhere on the internet, right? You would use a protocol called SSH, and you can SSH into that virtual machine, and you could do anything. You could install Linux, you could install Windows, whatever you want to do, you could do on that machine. You could maybe host a website, whatever you want. Now, let's say if you want to host a website, right? It's a new website, new e-commerce that you are launching, and you don't know what's the traffic going to be. So you just got this virtual machine, or rather this cloud server from AWS. Now December comes, it's Christmas time, and suddenly you have a massive amount of traffic coming in, right? So obviously, I mean, it could be like gigabytes of traffic that's coming every hour into your virtual machine, into your website. And of course, with such like 4 cores and 8 GB, it cannot handle that type of traffic. So you can go into your computer, go into Amazon Web Services GUI, and with a click of a button, suddenly you could upgrade this to a 16 core or maybe 32 gig, right? You could do that click of a button. That is the beauty of cloud computing, where click of a button, your server is now capable of handling this high traffic, right? So 1 month later, in January, your traffic goes back to normal, and again go back to your GUI, hit that button and downgrade your virtual machine to this lower version, right? And of course, because this is a concept of elasticity, right? It is elastic. So you could, depending on the need, you could increase resources or decrease resources, right? That's one of the features of cloud computing. And the other feature is you pay for what you use, right? So you could use whatever you want, and you can pay for what you use, right? So you could have that billing depending on what you use. So compare this with having a physical server that you buy in your office. So if you did not plan for that December surge in traffic, and if you bought a very basic server, of course you would lose your entire Christmas sale, because your server did not have enough resources to manage the traffic. But on the other hand, if you had planned for that December traffic, you buy a very expensive server, your server sits idle throughout the year. Only during these maybe 10 days in a year, it really makes use of its full potential, right? It's a waste of your IT budget. So that's why a lot of people are now going to the cloud, right? So when you talk about cloud, of course, like I said, if you do have the cloud virtualization with a hypervisor, you have on-premise cloud, or what you call the private cloud, right? That's a private cloud, but Cisco calls it on-premise cloud, right? So it is on-premise cloud, or Cisco just calls cloud, which is nothing but the public cloud, like an AWS server, right? So these are the two types of on-premise cloud and cloud, right? Public cloud and private cloud. Another classification is type of services that you get. So you would have cloud services as IaaS, SaaS, and PaaS. So whenever you say AAS, that is nothing but as a server. So I is infrastructure. So first type is infrastructure as a service. So like how we describe now, you could go into your cloud provider's GUI, choose what type of CPU you need, what type of RAM you need, what type of storage you need, hit that button, and immediately that virtual machine is alive, right? So that's IaaS, where you get an infrastructure. Next is SaaS, or software as a service, where you choose let's say for instance like Gmail, right? Gmail is a software service provided by Google, right? Now you don't care whether it was running on 16 core operating system, 16 core CPU with like 100 GB of RAM, or whether it's running on 2 GB of RAM. You don't care about that. All you're really worried about is the software, right? So you're only paying for the software. Of course, in Gmail's case, it's free. But again, there are a lot of softwares that comes as SaaS, where you pay for the software and you don't really worry about the hardware or the virtual machine behind. The next type is called PaaS. That is nothing but platform as a service. So platform as a service is very similar to IaaS, where only thing is here you would choose to have an operating system. You would choose to have few tools, because PaaS typically is used by developers. So you would say, I need this software, I need this operating system, right? So you would have that option. And here you're not buying the operating system. You're not paying, let's say for instance, Windows Server. You're not paying money and buying the Windows Server. You're only, let's say you want this PaaS server for 3 months. So you're just licensing it from your cloud service provider, and you're paying them for 3 months usage, right? That's the beauty of cloud, where you don't really have a lot of upfront cost, and because of elasticity, you could change the resources as and when you need it, right? Of course, we don't really have to go in depth into what cloud is and how cloud works. At the Ccna level, we're only just introducing you to what cloud is, so that when you go into your real jobs, you know what cloud is. So now we come back to our spine leaf, right? Now that we know what virtualization is, why you have a lot of east-west traffic is because, let's say we have, let me take another color. Let's say we have a server here, right? V server, and we have another V server, right? What if we have a reason where the physical hardware that this V server is running, right? Let's say this is a cloud and we are working for Amazon, all right, or one of these cloud service providers, and a customer has bought a IA server, right? So it's sitting on this physical server. Now, for some reason, we need to take this server down, the physical hardware. We need to take it down for maintenance, or it's broken down, right? It's not working. There is a problem. You need to take it down for repair. For an end user, what you could do is you could very well move this V server, or whatever that IA server that the customer has configured, from one physical hardware to another, and the end user will not even know that this is moved from one physical hardware to another, right? That's the beauty of your virtual machines, that you could just literally take that virtual machine, clone it, put it onto another hardware, and it would start working absolutely how you had it earlier, right? You wouldn't know. So because of all these type of moving, you have more of east-west traffic now, and spine leaf is an architecture that is ideal for this type of communication. So typically this type of east-west traffic is going to be seen more in data center traffic, right? Data center is where you would have these. Next, we'll be talking about Soho, that is small office, home office. So small office, home office, especially in today's world with all these pandemics, a lot of people are working from home, right? So when they working from home, typically they would have a small wireless router, like all-in-one device, which I mean, if you actually were to look at that device, if you were to actually look at these devices, this device actually has a router inbuilt, a switch, right? It has a switch. It has wireless access point, so we call it access point, and it has a very basic firewall inbuilt, right? It also has a basic firewall inbuilt. So all these together forms the access point, or rather router at home, right? Home. So these routers, of course, when you say router, it's a very basic routing function, very basic switching function, very basic access point, and a very, very basic firewall. So if you were to troubleshoot, one of the first things that you would have to look is the WAN link. So WAN could be anything. It could be 4G, 5G, it could be cable, it could be ADSL. Now with Elon Musk's company promising to give everybody satellite internet, it could very well be satellite, right? For somewhere there is a WAN connection that gives you internet access. So that is something that you need to first see. If there is no internet connection, that's something that you will have to troubleshoot. Second thing is, at the back of this device, of course, you will have a lot of switch ports, right? So let's say this printer is connected to one of the switch ports there, so you have basic switching functions. If you were to configure the device, typically you would take a wire and plug it to one of the switch ports, and it would give you an IP address, and you will go to your browser, type in that IP address, then you will get a GUI where you can configure everything. So router is configured where you go to the WAN section there, and then you configure the internet connection. Switch is straightforward. You really don't have to do anything, because once you plug in, these devices will start working. You would have to do little work for access point. So the difference between the access point that we discussed in the last video with a wireless controller is where the access point is called, typically when you have a wireless controller, the access point is called lightweight access point. That means it doesn't have any configuration options. The configurations coming from the wireless controller. But in this case, these are called autonomous access points, which means to say that the configuration also sits in this access point. So you would typically go inside there and you would configure the SSID, and you would configure the password, right? Once the configuration SSID and password is configured, anybody with that SSID and password can log into the access point, right? That's something you do. And of course, it has very basic firewall functionalities. Maybe you would have port forwarding, right? So you could have, if any traffic is coming from the outside, let's assume this has a WAN IP address of let's say 25.10.1.25, right? So if there is a traffic that is coming to port 1725, right? I'm just putting a random port. So if there's some traffic coming to this port, we could have a port forwarding option which says, okay, 1725 port should be forwarded to, let's say, we'll do this. So if there's any traffic coming in, we could say port forward it and send it to this computer, right? This is a functionality that you would do at the firewall level. So we know what routing is, we know what switching is, we know what access point is, we know what the firewall is. So once your SSID is configured, of course these devices would start emitting wireless signals, and now from your wireless functionalities of your laptop, you can connect to that device. So very, very basic things. These are something that we promised that we would be covering. So this is 1.2 that we covered now. And thank you for joining. We'll be coming back very soon, and then we'll be covering all the other topics that we have not covered. And then we will, like we discussed in a couple of videos ago, we will be filling this gap, and we would be ready for continuing our new CCNA, right? So all these information that we're talking now are part of your current CCNA, the latest CCNA. So we're just making sure that we bridge those gaps, right? So stay tuned and thank you for joining me today. We'll be back very, very soon. Bye-bye.